hoping it's still recording this. It should be. I haven't done this because I'm running Windows within Apple or whatever, Mac. So anyway, when you open up Visual Analysis, the button that's the most critical is the Help button, okay? The top right-hand corner, there's a little question mark, all right? And I'm going to give Adam a lot of credit for this because their help file is very extensive, super extensive, okay? So if you get stuck with something, okay, before you come and ask me how the hell do you do something, I want you to go out here and look at this, okay? Right? There's tons of topics out here about whether it's modeling, loading, analyzing, design, everything very well thought out. You can see I've clicked on things over time, right? All the purple shit. Okay. Welcome, James, man.
Thanks to Jacques.
Nice. Jacques didn't say anything about you.
I did.
He kept his mouth shut.
I didn't hear.
Oh, really?
Yeah.
I didn't hear. I wasn't listening.
Well, I already thought. So,
Okay.
50.
Yeah. So, help, right? If you get stuck, go to the help, okay? It's just like if you open up the steel manual and you get stuck, you go to the, what's that? Commentary. Thank you, Elias, right? Always go to the commentary. That's the one beautiful thing about ACI 318 is the commentary's right in front of your fucking face, right? It's right there looking at you, all right? Where AISC 360, it's in the back, so sometimes you forget about it, okay? So if you get stuck, go to the help file. There's stuff out there. What else? Oh, you know what I don't know that I did with the recording? It might just do screen and not audio. We'll find that out later. You guys are all here. All right. We start with the ribbon, right? We have file. Well, what can VA do? Well, obviously, we can save a project. We can create a new project. We can import things, right? You can import things from CAD. You can export things to CAD. You can import stuff from Revit, right? So how many of you have had experience with Revit? Right? Revit is like the drafting software for the architectural industry, right? And as structural engineers who work for architects, right, we get drugged into doing that unless you work at Hicks, okay? And you don't do that. You resist it, okay? But someday you will deal with Revit, all right? So what did Visual Analysis do? Well, Visual Analysis, along with other programs, I'm assuming, you can ask John when he gets here about RAM. Can you integrate between Revit and RAM? You can in VA, right? The problem is in Revit, I don't know if you guys are familiar, there's the physical model in Revit, and then there's the analytical model in Revit. And you can have it show you what they call the analytical model, which what it is Autodesk's trying to bridge the gap between modeling something and actually analyzing something. And at some point, I can imagine, they've already tried, making it an ability to actually do a finite element analysis of your structure in Revit. And so there's little line elements with nodes, okay, and those nodes can be oriented all over the place. So in Visual Analysis, for instance, when you're trying to pull in something from Revit, it's taking the analytical model. So what can happen, and it happens all the time to the point where it's not worth making this swap, okay, it's just worth modeling it on your own, in my opinion, or at least from my experience, is that there's problems with the analytical model from your physical model. And when it comes into Visual Analysis, nodes are off. So you got beams that are at an angle, things are oriented with respect to the grids, all because of those differences between the Revit physical model and then the analytical model that's done. And then VA pulling it in here. Okay. File, home. Well, what's in the home? Well, it's some of the more general and pertinent stuff with respect to file, which was edit. It's your edit ribbon, okay? So you can undo, redo, copy, paste, delete, stuff like that. One of the big things in here is load case manager and edit load case, okay? Right? As structural engineers, we have to deal with ASCE 7, or there's some Canadian load codes and stuff like that, right? So we have load sources when we load our structure, and this allows us to manage what those are, right? If we look at this drop-down menu, these are all the preloaded load cases, so what we call service cases, that Visual Analysis has built into it. Okay. Whatever is highlighted is what we see in the model view. Okay. If we want to edit this load case, right, the load case that's highlighted, in this case it's a service case, right, service case D. It gives us our name, where the load source comes from, include whether we want to include it in the analysis or not, right? Do we just want to pull it out for a second and not have it be part of the analysis? Do we want to put it into our building code combinations, right? Pattern ID has to do with building new load combinations. We won't deal with that. And then we talk about, well, as Stordahl talked, or Adam talked about with respect to that example where the guy stuck a building on the side of a cliff, right? The direction of self-weight and the use of self-weight can be very critical, right? In this case, we're going to put it with respect to the vertical axes. Well, we can do it with respect to some custom factor, right? Or we can put no self-weight on at all, right? Something to think about when you're modeling for this exam is the fact that and we did in the homework, okay, is that if you have self-weight, VA is going to put self-weight into your member as a energy equivalent load, right? It's going to be a uniform load acting with respect to the vertical axis, and it can skew your results, right? Because it's going to be incorporating this self-weight that in reality by hand, if we looked at a line element, we're not going to be including that, right? So we got to.
Factor is just like a percentage of it.
Yeah, you can factor it in all directions. So X, Y, and Z. You know, I'm not sure, Greg. Honestly, I'm not sure.
Like amplify or decrease your self weight. Why different like self weight and factoring it in different like?
I'm not sure. That's an interesting one. That's an interesting one. I'm assuming there's a catalyst for this, like something made this a reason,
Gravity in the
right?
direction versus the amount of gravity in the y direction.
Yeah,
This weird
I guess.
multi-
Yeah, if we're
direction.
designing something not here, I guess, somewhere else, another dimension. So we use the vertical axis, right? That's the default parameter. One other beautiful thing in visual analysis is every time you want it to know, well, what is included analysis? What does that mean? You hover your cursor over there, it'll give you a short description, right? Also, you could go to the help file, and in the help file, it'll talk about load cases and loading, and in there, it'll talk about service cases. It'll talk about what you can do with respect to our service cases, okay? Under structure, right? This is when we actually get to start doing things, okay? On the top left of this ribbon, we start getting options to draw things or create things, right? So we can draw nothing. What's the benefit of clicking this button? Well, now when I go out here, right, I'm not going to create anything. If I'm drawing members, if I click and drag, I've created a member, right? I can go back to the home, undo, and it's back to nothing, right? So we can draw members, right? These are 1D line elements like we derived in class, right? Linear axial displacement assumption, right? That's the field function that's assumed. It's a linear displacement in the axial direction. It's a cubic in the transverse direction, right? We developed those equations. And that's what it uses. So if we want to draw a member, we could just draw it. We can draw these areas, right? Areas we've talked about, they're essentially a plate without stiffness, right? It's just a means of distributing load to members, right? Or plates, right? Things with stiffness. We can draw plates. As I mentioned, you can draw plates with 3 nodes or 4 nodes. And if I drew a plate in VA, it has 4 nodes in it, right? VA is creating a node at the center, right? Automatically creates a node at the center and creates 4 almond triangles.
Is there any like, I guess, I don't know, value to knowing that about that center node? Like, just kind of seems.
Only in the results, because when you go to the results of this plate, see, this is how we could sit here and we could spend way too much time. Oh, fuck. Yes. I'm doing this for you, Elias. Where is it at? It should. Oh, it's this. Hold on. Self-weight should be acting in the vertical Y direction, so. Node results. It should be there. Why is it not? What it'll do is it creates the 4 nodes, nodes 1, 2, 3, and 4. And then it'll create this centroid node for the plate, right? The plate has a name to it also. So if we went to our plates, right? We generated one plate, that plate's P001. And when we get results, certain results, it'll give you what the magnitude is at the centroid, which is going to be that 5th node. And so you can use those results in some cases to figure out what's going on at the centroid of those.
Also, here's there's a stress compatibility among those triangles that form that plate. Just like in the result, it seems like there's like this even distribution stress. Maybe that's just the way it is.
Oh.
So it looks like there's discontinuities in between triangles. You can't see like the triangle lines or some weirdness, but maybe
Yeah, what they end up doing is this is our normal stress in the x direction, local x direction at mid plane. And so it allows us to, let's think here, sigma x, local direction, mid plane. I'll have to think about that some more, because it's true, it's an almond triangle, but the almond triangle gives you linear stress distribution, right? It's not the CST element. They added the drilling degrees of freedom, and then which allowed them to develop a displacement function, which is it'd be a second order. So that when you take the derivative of it to get strains, which give you stresses, it would be linear, right? So as you can see here, it's kind of that linear change across the plate. Does that make sense?
yeah, I guess so.
Okay. So, get back on track here, okay? So if I create a plate, right, I can create a plate that's either 4 nodes or 3 nodes in our structure ribbon, right? Lastly, we can draw cables. Well, cables are just that, right? It's like modeling a rope. You can only provide tension. It's just a one-way performing line element, okay? And so those are obviously helpful because in some cases, as structural engineers, we use cables, right? We use elements that are not two-way. They're not going to be able to endure compression and tension. It might just be tension, right? And so VA has put in a cable element to allow for that. Okay, so you can draw things, right? Draw members, areas, plates, cables. You can create members. When you create members, you have to give it a starting coordinate and an end coordinate, right? And so you can draw members that way. The way that I've always, for the most part, developed models is with creating nodes, right? So then you can create coordinates for each of your nodes, right? Buildings generally have grids, so you would lay out a grid pattern. You could establish, maybe you just establish the first floor, and then you can copy things up from there, right? And how do you copy things? So if I say we wanted to do a 0, 0, 0, we can go with, say, 10, 10, 0. We can go with 0, 10, 0, and 10, 0, 0.
Is there a way to turn that hotkey on so you can just delete it with your backspace?
Yeah, there's a lot of things in like preferences, which we'll get to in the tools ribbon for sure. There's a lot of changes you can make. changing colors of things and stuff. So like right now, right, my nodes I created were in the X, Y plane, right? And they're just a 10 by 10 grid. If I wanted to select all of them, I can hold shift and drag across and select all of them. I can hold shift and select one node. It selects all nodes in our model, right? And if I wanted to copy, I could either use the ribbon, right, the home ribbon, or we can just control copy, control paste, right? Control C, control V, or do copy paste. What does it allow us to do? Well, it allows us to copy our model objects. Okay, we can use a rectangular pattern. We can do circular pattern, we can mirror things, linear patterns, all sorts of stuff. You tell it how many copies you want to make in the X and Y, you give the spacing, right? So if you had a grid for a building, maybe it was a 10 by 10 grid and the building was 100 by 100, you could create all the grids on the first floor, right? Or even you could create one node at the origin, right? And then start copying it across, and then copying it up. There's many floors to do that, right? That's fairly straightforward, pretty simple to do. And so if we wanted to control copy, control paste, I'm gonna do, say, one copy in the Z direction. I'm gonna make it 120, right? All right, now this is showing inches. Okay, if I wanna change units, right, you can go up into the ribbon here in the home, and you can manage units. They have unit styles. You can add your own style, right? And when you pick a style, it tells you, right, what its units are for all of these parameters, right? Material properties, dimensions, geometry, stuff like that. Oh, that's why we're gonna do this. My model's been in inches this whole time. So make sure you watch your units, right? I assumed I was in feet when I first started, so my little 10 by 10 is really this 10 inch by 10 inch square, right? Copied it up 10 inches. So now we have this 10 by 10 cube. If I wanted to draw members now, right? And as you can tell, well, you guys can't really tell, but it's showing us one of the big things in visual analysis is this project manager window. Right? The project manager window, it allows us to do a lot of things with respect to this model, result, design view, and report view, or the viewer window. Okay. When we're not selected on anything, we can modify, right? In our modify tab in the project manager, we're really modifying our project settings. Right? And as we know, when we look at like further analysis in structural design, there's a lot of things that have to do with seismic loading, design checks, right? We can add titles to our reports, okay? Nodal tolerances, well, this comes into play sometimes if we're bringing stuff in from Revit or you're generating and copying things, right? Visual analysis actually will make one node out of two nodes that are closer than 0.0625, right? If they're just off by a little bit, they're gonna assume that they're the same thing, okay? They're gonna have some little nodal tolerance. As I mentioned, there's all sorts of stuff in this project manager, and we'll continue to step through this. But just know that this is kind of the project settings for the overall project. Okay. Well, what some of the big things with respect to self-weight is we have this vertical axis, right? Well, I kind of modeled mine with respect to having Z be the vertical axis. So you can change that, right? What does that change? Well, it also changes the direction of the self-weight, right? If you remember in the dead load service case, we had the vertical axis being the direction that the applied self-weight is in, okay? We can also change the orientation of our project. You know, it's gonna say that, okay, now if the Z-axis is vertical, well, that means the plane axis or the plan views are in the X and Y direction. And we can orient our model similar to what we would orient in, say, Revit, okay? We can change coordinate systems if we're doing, we could model a sphere, right? A spherical tank. We could model a cylindrical tank. And we're modeling a cylindrical tank, sometimes polar coordinates are a lot easier, right? A radius and an angle. sort of thing, versus using Cartesian or the X, Y, and Z. All right, what else we got? So we're back to the structure ribbon, right? We can generate all these things. Some of the extra stuff that's not highlighted here, and mainly it's because I don't have things there to generate it, but we can add spring supports, okay? We can give our model, right, say a torsional spring or a linear spring. What would that mean? Well, so have you guys dealt with like side plate systems? Have you heard of side plate systems? Okay, it's a proprietary system that what they do is they come in and for a moment frame, instead of doing, you guys take an advanced steel like reduced beam sections, RBS, where you do a dog bone, essentially in a moment frame, in say higher level design, like special moment frames for instance, we as designers want to make sure we know exactly where the hinge is going to be, and we're going to want to make sure that that hinge is in the beam and not the column. Strong column, weak beam behavior, right? So what do? Well, we trim the flanges down. Well, side plate came in and said, okay, instead of trimming the flanges down, let's just make the connection between our beam and our column super, super strong, okay, and force that failure out into the beam somewhere. So you end up taking your model, sending it to side plate, and they go through and they add spring supports. So now instead of having, right, essentially the resistance of just the beam to column intersection, so if we want to draw beam, create members, draw members. Drew a member. So now we essentially have this pedestal, right? So if we look at these three members, right, they create a moment frame. We pushed on this table to the side, right? The resistance to pushing is going to be based on the boundary conditions at the bottom, whether it's fixed or pin, and then what type of resistance we have here. And what side plate does is you can put a torsional spring in there to account for the added stiffness of putting a bunch more members at that connection, right? So instead of just being a W12 by 26 framing into a W14 by say 43, you can increase the stiffness there, and so VA allows you to do that. You can create spring supports, right? If you don't feel comfortable about saying that the base of your structure is going to be fixed in the vertical direction, right? We have columns land on footings which land on dirt, right? Well, those are not infinitely stiff in reality. So what you can add is you can add spring supports there. Or what VA allows you to do in the next tab there is you can generate soil springs, right? Some of you have taken geotechnical structures maybe, or geotech, right? You have the modulus of subgrade reaction, okay? It's in pounds per cubic inch, PCI. Usually it's about like 200 to 300, okay? That is the pressure per inch of displacement, okay? Pounds per square inch per inch of displacement. VA allows you to generate springs based on that, which you would get from a geotech report, right? Which would be a lot more accurate than saying that it's infinitely stiff on a foundation. Okay? You can do some stuff where you create some areas, all right? Another big critical part of drawing is our local axes, okay? When we do local results for our members, it's based on local axes, right? And we know from deriving our models, right, our elements, we know that the local coordinates need to be transposed into or transformed into global coordinates and vice versa. And the direction of those coordinates make a lot of difference in what the results read, right? Whether this beam, the axis is this way versus axis going this way, right? It becomes a real big thing if we had multiple beams in a row, right? We might have an axis that runs one way and then an axis runs the other way. You might want to report those in a series, and you're going to say, holy shit, the force flips direction. Well, why does it do that? Well, it's because our coordinates changed, right?
So based on how you draw the direction.
Yeah. So if we do the model filter. So in this project manager, right, there's the modify tab. The modify tab allows you to modify project settings when you're not selected to anything. If you select a member, right, that member obviously has a name. You can change that. You can change what type of member it is, what shape, what material, how it's connected. Underneath the model filter, okay? Under member details, you can see local axes, right? So now it starts showing us what is the direction of our local axis. So if I wanted to, say we just wanted to build a frame, right, just like this, and we were going to apply some loads on it, right? Say it was sitting outside, say it's the frame that's sitting over the HVAC system out here, right? 4 columns, flat on top. We would start by drawing our members, right? We have columns, we have beams that interconnect. If we wanted to know what those shapes are, we can have it tell us what those shapes are, right? So that's where the model filter is very helpful in showing us what we can see in the viewer, right? Sometimes things can be hidden and then you can assume something and it's not right. Another thing that's helpful here is underneath the home tab is this picture view. Holy shit. It's because the size of this model's 10 by 10 inches, right? And my members are like 12 by something. So it just kind of gets dominated here, right? But you can tell this takes into account the actual geometry of the shape you selected, okay? So if these were wide flanges, you'd see a little wide flange. What's the helpful part about this? Well, this helps us understand if we needed to rotate something, right? If we were expecting that this is acting in the strong direction, for instance, in a moment frame, we better make sure that it's actually oriented in the right direction, right? And so the picture view is a helpful tool in order to just jump back and forth to make sure that what you're drawing is actually makes sense. So in picture view, that's scaled too, right? So if I drew this assuming my units were in feet, and then all of a sudden I went to the picture view, this would help me realize that something's fucked up, right? Like, oh, I did something wrong, right? All right. What's critical with, say, a frame of this nature is our releases, right? We talked about in class the idea that we have shear tabs, which might not transfer rotational stiffness, but we have translational stiffness. Okay, moment frames, it would translate full stiffness, right? Which is what our elements are derived based upon, is transferring of that stiffness between one element and the other. Well, in order to get rid of some of that, we can select our member, and underneath this connection type, we can change it to simply connected. What does that do? Well, it shows us these little circles. And these little circles, when it's simply connected, that means that it can rotate in both directions freely, right? So there's no force transfer with respect to moment at that node at the ends of that member. What would be an example of something that we would release other than a shear tab? Truss, brace frame, yeah, exactly. There's a lot of other cases where we would not want to transfer moment, right? Or we would design it as such. In this case, right, if we released both of these, say they're simply connected, this is unstable, right? If we pushed on this table, pushing this way, this thing is just going to fall over, right? Unless we had it fixed at the base. So how do we add fixity at the base? Well, when we select a node, we can decide underneath the project manager under modify, right? We can modify that node and we can determine what type of fixity it has, right? So right now, it's free to translate, right? Displacement X, Y, and Z, rotation X, Y, and Z, and it's free to translate or rotate in all 6 degrees of freedom, right? If we want to fix them, we can either go through and fix each of them individually, or under here, we could fix it. What does that mean? It just automatically checks all the boxes for us, right?
Changing that support condition that, or like, I guess instead of going and like doing the releases and you say simple support, it does that automatically, right?
So yeah, so that's a very good question, Elias, right? So if I pin this, and then I also took this column, and I made it simply supported, simply connected, and I'm going to select the rest of these. If we look at this column by itself, right? It's pinned at the base, and it's free to rotate, right? So it cannot have a moment at the end of this member in the two directions, right? In the X and Z directions. Right? What does that do for this node? Do you see a problem with the node? It can spin, right? It can spin in this direction or the other direction. Essentially the weak axis and strong axis bending of the column. The node can, right? Because, what's that? I did, and then I made it pinned to show Elias why pinning it and releasing it are bad.
But pinning it, like, I guess I'm thinking about the axes, is it assumes when you say simple support, like on those beams, you say simple support and it knows which axes should be free to rotate and like along its axis, I guess.
When you do simple support, what it ends up doing is it releases the strong and weak axis, right? You could go through and say, this gives you a fast way of imposing all of these releases.
Right.
What if you have a fixed node but released member?
Then that's okay, because the node is held in place, right?
Then can't the member just spin around the node in both directions?
Well, that would be like a global stability thing you'd have to take into account, right? Because, yeah, I mean, if you fix this node, and this was just a cantilevered column, it just stood up here, we erase everything here, right? If this was a fixed node but it was released, this column could just rotate around in the two directions. Because it can't provide any force there, right? We're saying that it's released.
There's no difference between the member and the member, right? Like, just making it simple supported releases, it's all nodal releases, or like, what's the word? I guess like all of it has to do with the node, there's like no difference between node and member boundary issues, right?
True, but we are providing, in visual analysis, the way they separate it is when we provide, we're looking at the member and releasing its ability at the end to connect to that node. Which is essentially, it's doing the same thing. I see what you're saying, Liz. Yes, like the fine.
That's not even in the math, right? Like there's no.
No, agreed, but this is like more of the user interface part of this. Essentially, right? If it was buried in the node, we would select the node and say, how is it released, right? But in reality, if we select this node and we say that it's pinned, right? It's not going to fix that node in space, right? It's going to have no fixity. But again, the element that we connect to that node, because the node can be connected with different types of elements.
Yeah,
Right.
if there's multiple rows that one jump, like
Yes.
you want to release one beam but not the other.
Right? Does the stiffness of that member affect the stiffness of that node, or does it not? Because in this case, this column is
Because that
not
column was
affecting
fixed
the
at the bottom. You fix the node at the bottom, and then you click the column, and then you did simple connect, and then it unreleased the bottom node. Like saying simple connect, column released the nodal fit like fix it.
No.
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 Because there used to be those two circle.
You changed it.
You changed it.
That's what I was asking.
Yes. This is denoted as a pin, right?
So there is a difference between saying like type and releases.
Yes, releases are attached to the member, right? The element itself, in this case, the line element that we're connecting to it. And then on the node side, we're providing what type of connections, right? The support conditions that node has on it. So in this case, it's pinned. We said it's pinned, so it's fixed in the X, Y, and Z directions. Right? But it's free to rotate. So that node can rotate. And if we don't have it connected to an element, which is what we're saying there, we're saying that that line element that's connected is not allowing force to be transferred, then it's going to allow this node to spin, right? Because it cannot keep it from rotating, because we're saying that this line element that we're connected to it has no fixity with respect to rotations. Hopefully that makes sense.
So if you just get rid of the circles on the member, then you're good on that connection. Like you can pin it.
Yes, because then it would connect it, and then that node has some means of fixity between it and the element.
So could you either pin the node and not release the member, or fix the node and release the member?
Sure.
And-
Yep. Yes, but in this
That was
case,
my thought.
Yeah.
in this case, if you had, like Amanda was saying, multiple beams framing into one node, you wouldn't want to fix that node because, I mean, that fixes it in space
Yeah.
to where you would essentially, if that node, if you wanted to fix this one, for instance, right above here, we've got multiple members framing in. If I release this one, for instance, right, simple connect. So I have 3 members framing into one node and they're all simply connected, right? So that node can spin, right? And move, right? It's connected to the elements in that it can it's going to translate with the elements, but it's not going to rotate with the elements. Okay? And so that's why you wouldn't want to fix this pin, this node, right? Because then that truly fixes it in
Fixes
space.
the displacements. You
Yep.
can't displace.
So you're just going to essentially, Adam has an example of somebody that called in and says, I'm getting no displacements in my model. And they fixed every node in their entire model. Okay?
That's more intuitive than thinking. It's like hard to think of something that would induce a node to spin, like a load that would cause one node
It's
to
not
spin.
necessarily inducing it to spin, it's an instability, right?
Yeah.
It's not restrained. And so then it ends up screwing up the stiffness matrix, making it singular. You can't take the inverse of it, and then something goes awry. But as Adam said, if your model gets very, very large, it's doing a lot of operations to get to that stiffness matrix. And based on the fact that we have to truncate at 16 decimals, right? There's the ability to have a very, very small. It could be 0.000001, and that gives it enough stiffness to where it would run. But then the next time it might not run, right? So and it might not give you the results that you want. It's going to give you results, but as Adam showed on that one, it was a frame that looked just like this, right? And what the guy had done, the person had done, was fixed the beam in one direction, right? So it had moment resistance, but then in the other direction it was all released, right? So this thing would just lay flat. And it did lay flat, right? That these nodes traveled 7 light years out one direction. Because the stiffness was so small that the displacements that it ended up calculating were massive. Right? So again, going back to validating your models, like, does that even make sense? That would not make any sense.
Written, you can fix all of your nodes and then release all of your connections to those nodes at your base and get invade. Like, I feel like you're gonna miss out on something there. You know what I mean? Versus pinning all your nodes with fixity to the pin. You know, you can go like either route.
Yeah.
Behavior. Like, do you lose anything in the results?
You shouldn't lose anything in the results, right? Because you're essentially modeling the exact same behavior, right?
Just 2 different ways.
Just 2 different ways. I mean, that's the creative art side of modeling, right? I mean, like, there's a lot of different paths to get here, right? And you can do it a lot of different ways. Okay? So where are we at now? All right. So we can load members, right? So if I wanted to apply a member load, this thing's all screwed up. We're going to just I'm going to make them all rigid. I'm going to fix all the bottoms. Okay, right? So what does this model, this says that at those beam to column intersections, all of those members are rigidly connected, right? If that node rotates, all of the members that are connected to that node rotate the same amount, right? In any direction. Right? If it translates, all of those elements translate together. And at the base, we just have it all fixed, okay? And so we can apply member loads, right? So apply member loads, you can right click on them and apply member loads. You can go up here, click on this, go up to the loading ribbon, right? It'll give you a selection based on what you select, right? Give you the ability based on what you select. So in this case, I want to apply a member load. And apply a member load. A window pops up, allows you to do all sorts of stuff, right? So now, in all of the predefined service cases, I can apply a load, right? And it's going to dump that into the service case. If I apply a load right now in the live load case, I can say that it's a single point, uniform, linear, there's all sorts of different options, okay? So if I did a single point load, shear in the Y, right? Small case means local coordinates. Big case means global coordinates, right? So you can, depending on your local coordinates now, right? If I did shear in the Y, it's going to be loading that in the out of plane direction, right? Shear in the Z, in the vertical direction. I try and do global when I can because it makes things easier for me. Single point load, you can do an offset right now. That's the mid span, right? This was a 10-inch by 10-inch frame. You can do a kip, so I'm going to say that I'm going to put -1 kip on this thing. I press OK. Where the hell is it? Right? It's not there. Exactly, right? So something to be aware of, okay? Your model view is only going to be viewing the service case that you are selected, right? Now this service case popped up because there is an actual load in it, right? So it'll become available when there's loads in it. Now I go to the live load case and you can kind of see it here, right? It's that little yellow guy right there. And we have a point load sticking on the member in the Z direction. So we can do all sorts of loads in all different directions, uniform, point loads, okay? We go to the results view. Results view, nothing's happening, right? Or it appears that nothing's happening, right? These are 10 inches, these members are massive. Yes, Daniel?
Yeah, so it doesn't matter even if you apply a member load at a place that there's no node.
Yes, correct, it's fine because just like we did in our elements, right? We had a point load that was between nodes. Visual analysis,
Then
VA
you take
goes
care
through.
of taking that.
Yep, it does the energy equivalent loads and it moves that point load out to the side, just like you did in the homework, right? Well, this doesn't look like it did much. Well, this was our dead load case. Well, if we go to the live load case, right, you can see that we've got a slight bow in that member, right? We have that 1 kip load sitting here, okay? You can see, you can do undisplaced. Again, this project manager is very powerful and it allows you to filter what's going on. Well, I want to show, say, the undisplaced. You can kind of see what's going on. That side of the frame is displacing downward, right? That beam is kind of has a curvature to it. This kind of makes sense, right? I assume that that would be the case. We can do all sorts of crazy stuff with respect to member results. We can have it show us the shear force. Well, let's do the moment in the Z direction. And it highlights what's going on in the Z direction. Can give you moment in the, I mean, there's so much shit to this. Right? This makes sense, right? This would be our moment in the Y direction, so that's bending about the Y axis. You can imagine it's going to be greatest in the center. You got essentially a fixed beam with a point load at the center of it. Okay. You can take it a step further and you can select your member and you can report the selected, or you can do what's called a member graph. So if you go over here and you hit member graph tab, now it's going to give you 3-dimensional beam, but we can do custom plots. You can do displacements. You can do all sorts of stuff. This is going to be very helpful in the exam. So we have dy, we have dz. Let's see, it must be dx. For which member is this? Is it dy? dz? Wow, those are very, very small displacements, aren't they? My, so it gives you your curves, right? You can do the axial loads in the exam. You're going to have the axial, shear, and moments. Okay, so we can confirm or validate your results based on modeling. Okay. Questions? Kind of seems like this is time.
Can you put one of those plots like in the model view or show you?
No. Nope. You can. Oh, in the results view?
Or results view, yeah.
You can do, it will actually do, instead of colors, you can do diagram. So I can do that. Yep. Okay. So for the exam, last question of the exam. asking you to validate your solution with visual analysis, okay? You just, it's not a frame or anything like this, okay? It's a very simple little stair stringer kind of model, right? If you have any questions about modeling, I'll be around, okay? But it'll help you to validate displacements, reactions, and finally shear moment and axial loads in your member, okay? Any questions? So I'm going to give this to you, okay? Again, individual me versus you 7, okay? I don't want you teaming up with anybody now. There is 18. Sorry, 17 kind of short answer, 2 a little bit longer answer, and 1 super long answer. Due by the end of the day, Wednesday. Okay. You can use the notes. Don't use the book. Don't use the internet. There's some extra credit. Do you have any questions, okay, about how it's presented? Please come talk to me, okay? See anything on the last? Let's just jump to the last problem so I make sure that I'm squashing it, hopefully. Okay? So the last question. This might be a stair stringer type model, right? Where we have a stair stringer that's running up the stair angle, right? And it's flat at the top. I'm providing some loads on this stair stringer, right? So it's a 2-element, line element model. It's fixed at nodes 1 and 3, right? At node 2, it's free to translate and rotate. No releases though, right? So those 2 elements are fixed together, okay? We've got a point load at a distance m. That point load will give you a magnitude of 8 kips, right? So it's acting in that direction. The moment I give you a magnitude of -175, what does that mean? Well, that means it's acting in the opposite direction of what's there. Okay, I drew this, copied it, and then I was like doing it, and I'm like, fuck, I want it to go the other direction. So just know that that moment should be applied in the other direction. Okay, the uniform load, it's acting in the global y direction, right? So that W is acting vertical. Okay, the global sense, not in the local sense, global sense on element 2. I give you a magnitude. I give you the lengths, right? In the horizontal direction, you have 2 15-foot distances, okay? And then the height of this stringer is 10 feet off the ground, okay, at element 1. I'm going to ask you to calculate global displacement and force results, right? So we did that in your line element, or your axial element homework, right? The whole process, we go through and we establish the local stiffness, and we have to come up with the global stiffness, and we have to impose boundary conditions and things like that, right? Then I want you to sketch what that looks like. You don't have to plot that out in MATLAB, okay? You're going to get displacements and forces, right? You're going to get a displacement matrix that gives you rotations and translations of each of your nodes, right? You can just quickly sketch that out, okay? By hand, yep, just to show what those are and just label those. Second part is calculate the global reactions at node 1 and 3 and indicate those on a sketch, right? You need to do that, it's obviously straightforward. Now using mechanics, plot the internal moment, shears, and axial forces in element 2. Right? So as we know, we don't have intra-element compatibility, right? When we do this in VA, or in finite elements, we have linear strain, like linear displacement, which means we have constant strain, which, as we remember, if I drew that little free body diagram, we don't have equilibrium along the length. Okay? In order to get that, once we know nodal values, we can use mechanics and get our own, right, expression for the axial load, the shear, and the moment within the member. Okay? What does mechanics mean? Draw free body diagram. Okay? Draw free body diagram.
So we're using like a variational beam and making an assumption
Yes, you use
Plane
the,
stress or plane
we
strain.
use, you will be using the variational beam element that is, that also incorporates axial load, right? Because in our, I keep thinking it's up here, right? That uniform load W is acting in the global Y direction. That's acting in two local coordinates, right? So we went through and I gave you the shape functions, I gave you the matrices, it's all in the notes for how that works. The derivation is the exact same as the axial load, but.
When you
homework.
say exaggerate the displacements, does this mean you want a scale factor?
I would just say that because I was trying to make it easy to say that you can sketch it and you
Oh.
don't need to plot it in MATLAB. Okay? So I don't expect it all to be to scale. Okay? And then at the very end, probably the most important part of this whole thing is you're gonna verify your results through visual analysis. So you're just gonna model this two-member model in visual analysis, right? We just went through how to apply loads, we just went through how to provide fixity at nodes, all those things. You can go through the results. It's going to be able to give you the displacements and forces, right? Or reactions. VA will give you those. It'll give you the global reactions at nodes, right? We're gonna have reactions at node 1 and 3. And then we're gonna use visual analysis to plot, right, the internal forces, axial moment and shear. Okay, and you should be verifying. I will tell you, you should get the exact same answers. Okay? Which makes sense, right? It's all based on what we have done in class. VA
Do you have
is the
some
same.
more like advanced things like displacement induced stresses and stuff like that?
I mean, you can do different analysis types, whether it's first order or second order. Okay, like P delta stuff, where it takes into account, like we went through in the notes, the coupling effect of axial load when you start actually displacing something. You start getting strain energy associated with that axial load. Or if you assume the displacements are small, you don't. Okay. We'll talk about, after the exam, we'll talk about how VA does internal forces.
Like on Adam's example with like the rafter thing, the displaces was only connected at those 4 nodes. Like the displacement of that plate would not induce any like load on those.
Nope, because they are
It's
only,
underneath,
elements are
right, so there's
only
no-
connected at
So it
nodes.
just displace through the element.
Yep, you would look at a displaced shape diagram like we just did here, and it would be,
Right through it.
yep, they would not be the same.
Not the P and W acting the way they're drawn up.
Yes, P and W are acting the way they're drawn. Yes. Yeah, sorry about that. I was finishing this up last night and I was like, fuck. Because the displacements were not what I wanted, and so I changed the direction of it.
How long you are storing answers to?
Long enough to give me the right answer. I'd like you to put it on a different sheet,
Yeah.
okay? Because I don't think you could fit what I'm asking you on this sheet, okay? Amanda, I know how you like to compress everything. But I don't think you can get it on
I
this.
don't know.
Okay.
Did you say you used MATLAB for the first test?
Yeah, so the first part of the last problem, problem 20, you're gonna be writing code in MATLAB. Right? I'll tell you, it's very similar to what you guys did for the axial member. Right? But now we just have a different element.
You have to use MATLAB? I mean, can you use a calculator that can solve it?
I'll be
Like write it
curious.
out by hand?
Yeah, I mean, if you wanna, yeah, sure. But I want the sequence, right? The finite element analysis approach, which would be local to global, back to local sort of thing, right? Where we start with our stiffness matrices that we developed in class, right? For the local level, and you gotta put them all, you gotta assemble it, right, based on the elements, okay? All that sequence needs to be there. You can go out and, I mean, the homework solutions are out there, you can look at those. Homeworks are out there, right? So my code that I use for the axial bar is out there. Right? Start with that, if that makes sense to you, whatever. Just don't use the text, you can use all the notes.
Yeah, why is that one?
I don't know, I don't wanna, don't muddy, you don't need to, I guess. I don't think that is going to benefit you. We do have a text. We do have a text, Aaron. Yeah, we do. Yeah. Jesus. Send me an email. Stop by my office.
Oh, dude, I can't figure it out. It's like such a mother.
I just ordered it like last week.
And so you go to the thing, it's like create an account, and I already have an account, so I go to like change password, and I change the password, then I log in, and then I'm not at that page, so I can't do it as well.
Yeah.
It'll take you where you can't.
Once you're logged in, I've done that.
Like, once you change
You
your
log
password,
in.
and just go like back over there, you're gonna like the link in the announcement.
Click on it again.
Yeah.
I'm pretty sure I just clicked on it like 20 times and one time it worked.
I swear to God, I've done that so many times. I gave up, sent Vic like an angry email.
No, I emailed it and I see anything that I clicked on, like you're.
Oh. You had the same thing too. I just like clicking on random things for an hour and then just like routing me to the correct page one at a time. It's weird.
I've got one in my office too.
Oh, yeah.
Okay, yep, see ya.
Yeah.